In Shangyin County, in China's Hunan province, a line of trucks pulled up to an empty site carrying what looked, from a distance, like ordinary shipping containers, 12 meters long, 2.4 meters wide, 3 meters high. Stackable, craneable, the exact proportions the global freight industry has used for 70 years. But these boxes were not steel plate wrapped around a plywood floor. Each one was built from a material made of 2 sheets of stainless steel, with thousands of thin steel tubes brazed between them. And one entire wall of every box was designed to swing down and become the floor. 5 days later, 26 of those boxes stacked on top of each other were a finished 26-story residential building with water, power, and air conditioning already running inside it. If that material ever gets cheap enough to sell one box at a time, the container home you have been pricing out on a spreadsheet, the one built around a 40-foot steel box originally designed in the 1950s to carry cargo across an ocean, could end up looking like a very clever workaround for a problem that no longer exists. Here is how it works, why it took this long, and why it is harder than it sounds. Take a second and think about why container homes became a thing in the first place. The pitch is almost perfect. There are millions of steel boxes sitting in ports around the world. They are already engineered to survive salt spray, ocean storms, and being stacked 9 high on a moving ship. They come in standard sizes, so they fit on trucks and trains anywhere on the planet without a permit. And you can buy one used for a few $1,000s. It is one of those ideas that sounds too good to be true the first time you hear it, and it caught on hard. The global container house market was valued at more than $50 billion in 2022, with industry projections putting it near $68 billion by 2026. Prefab container homes typically sell somewhere in the range of $50,000 to $150,000, and build cost usually lands between $150 and $350 per square foot, compared to roughly $200 to $400 for conventional construction. That gap is real. It is also narrower than most people expect. There's actually a much bigger story behind all of this that I couldn't fit into this video. So I put it together in an ebook for anyone who wants to go deeper. You can find it in the description or scan the QR code on screen. Now let's get back to the video. And here is the thing almost nobody says out loud. The shipping container was never designed to be lived in. It was designed by a trucking executive named Malcolm McLean in the mid-1950s to solve a completely different problem, which was that loading loose cargo onto ships by hand was slow and expensive. Every design decision inside that box exists to serve cargo, not people. And when you try to move a human being into it, every one of those decisions becomes something you have to fight. Start with the structure. A shipping container is strong in a very specific and very narrow way. Almost all of its vertical strength lives in the 4 corner posts and the corner castings, which is what lets you stack loaded containers on top of each other. The walls themselves are thin corrugated steel, usually around 1.5 to 2 millimeters thick, and the corrugation is what gives them their rigidity. That is the whole trick. Fold a flat sheet into waves and it stops behaving like a floppy sheet. Which means the moment you cut a window into that wall, you are removing part of the structure that made it stiff. Every large opening in a container home has to be reinforced with welded steel framing to put back the strength you just took out. Cut too much, and you are essentially paying a fabricator to rebuild a structure you bought specifically because it came pre-built. Then there is heat, and this is the part that quietly ruins more container projects than anything else. Steel is an excellent conductor. That is a wonderful property in a saucepan and a terrible one in a wall. In a container, the metal shell runs continuously from the outside surface to the inside surface with nothing interrupting it, which building scientists call thermal bridging. Heat simply walks straight through the metal, bypassing whatever insulation you installed, and the more insulation you add on the inside, the colder the steel skin behind it gets. When warm indoor air touches that cold steel, it hits its dew point, and water condenses on the inside of your wall. Not occasionally, continuously, through every cold season. That is where the rust and the mold stories come from, and it is not a construction defect, it is physics doing exactly what it should. And then there is the floor, which is the part people tend to discover last. The deck of a shipping container is usually marine plywood or bamboo laid over steel cross members, and because that floor spends its working life in ports and holds where insects travel between continents, it is commonly treated with pesticide compounds to satisfy quarantine rules, which is entirely sensible for cargo and something you have to seal over, cover, or remove entirely before anyone sleeps on top of it. Underneath, those steel cross members run continuously from outside to inside, which means the floor is a thermal bridge too, and one that most conversions under-insulate because it is the hardest surface to get to once the box is sitting on its foundation. Even done properly, industry guidance generally puts a well-built container home at something like 25 to 30 years before major maintenance, which is a respectable lifespan for a repurposed cargo box and a short one for a house. The standard fix is to insulate on the outside, wrapping continuous rigid foam or mineral wool around the entire box so the steel never gets cold in the first place. Which works. It also means you are now building a second, insulated structure around the container you bought to avoid building a structure. And on the inside, if you insulate there instead, you lose interior width in a box that is only 2.4 meters wide to begin with a ceiling already low enough that most people notice it. That is the compromise at the heart of the whole category. Every solution to a container's weakness eats into the advantage that made you choose a container. So a reasonable question is the one Chinese engineers appear to have asked at some point, which is this: if the shipping container's shape is the useful part, the stackability, the truckability, the standard corner castings that every crane on Earth already knows how to grab, then why are we still insisting on the cargo box itself? Why not keep the shape and throw away the material? That is roughly the idea behind a structural material called B-Core, developed by Broad Sustainable Building, part of the Chinese industrial group Broad, which spent most of its history making absorption chillers and air conditioning equipment before it moved into construction. And the material is genuinely strange in a way that is worth slowing down for. Picture two flat sheets of stainless steel, held apart by an array of thin-walled stainless steel tubes standing between them like a forest of tiny columns, all fused into a single panel. According to the company, the fusion is done using copper foil laid between the tubes and the plates during brazing. Because copper melts at a lower temperature than stainless steel, it liquefies first, flows into the joint, and solidifies as a bond, while the steel itself never melts. The result is one continuous piece rather than a bundle of parts held together with fasteners. The reason it is stiff is the same reason a bridge truss is stiff. When you load the panel, the top sheet goes into compression and the bottom sheet goes into tension, and the tubes in the middle hold those two surfaces apart at a fixed distance. Bending strength depends enormously on how far apart the material is spread from the center line, which is why a hollow tube is so much stiffer than a solid rod of the same weight. Spread the steel out, keep the middle mostly empty, and you get a panel that acts far thicker than the amount of metal in it would suggest. The panels are made anywhere from around 1.5 inches to 15 inches thick, with 4 to 6 inches typical for buildings, and the empty space between the tubes gets packed with rock wool, which turns the structural panel into an insulated panel at the same time. The company says the idea came from outside construction entirely. Brazed honeycomb stainless panels have been used in aircraft manufacturing for years, where they are prized for being light and strong, and where, by Broad's own account, they cost something in the region of $3,000 per square foot. The engineering goal was to get a similar material out of the aerospace price bracket and into something a building could afford. Broad's public claims for the finished material are aggressive. The company describes B-Core as roughly 10 times lighter and 100 times stronger than conventional alternatives, and states that stainless steel gives it over 30 times the corrosion resistance of carbon steel, which is the material a shipping container is made of. Independent engineering analysis of the published panel data, notably by the writer Brian Potter at Construction Physics, found the raw strength figures impressive but noted an important caveat. Thin, strong floor systems are usually limited not by strength, but by deflection, meaning how much they visibly sag, and once you apply standard American code deflection limits, the maximum span drops to something like 34 feet for a 6-inch panel and just under 26 feet for a 4-inch one. Still very good, considerably less dramatic than the headline. Now, here is where the shipping container shape comes back into the story. Broad did not use these panels to build flat walls. It used them to build volumetric modules the size of a 40-foot-high cube container, with B-Core forming the floors, the walls, and the roof. Each module leaves the factory finished, with wiring, plumbing, insulation, glazing, and ventilation already installed. On site, cranes stack the modules and workers bolt them together, and then one side wall of each module unfolds downward and locks into place as a floor plate. Two modules facing each other and unfolding toward each other produce a single-column free room roughly 12 meters by 4.8 meters. Windows and balconies fold out from the same unit. When it is folded shut for transport, the whole thing is container-shaped on purpose, so it can travel on the existing global shipping network without a single custom permit. The assembly method is worth a sentence of its own because it is the opposite of how buildings normally go up. There is no concrete in the structure at all. Modules are joined with a bolted connection system rather than poured joints or extensive site welding, which removes what builders call the wet trades, the parts of construction that have to cure, dry, and wait on weather. Remove those, and the schedule stops being governed by chemistry and starts being governed by how fast a crane can move, which is why the company quotes installation rates measured in floors per day rather than weeks per floor. The envelope is handled in the factory too, built toward passive house principles, with triple and quadruple glazed windows, external sunshades, internal thermal shades, rock wool insulation, and energy recovery ventilation, with the company claiming very large reductions in air conditioning energy as a result. Take those claims as manufacturer claims rather than independent measurements. But notice what the approach does to the specific problem that plagues container homes. Instead of buying an uninsulated steel shell and then fighting condensation with layers added afterward, the insulation is inside the structural panel from the moment it is manufactured. The thermal bridge is not patched. It is designed out before the panel exists. That folding trick is the part that reframes the entire container home argument. A shipping container home is limited to 8 feet of interior width because that is how wide a container is, and no amount of clever interior design changes that number. The unfolding module ships at container width and then roughly doubles its floor area on site, which means the transport constraint and the living constraint have been separated from each other. The box is no longer the room. The box is just the delivery format. The demonstrations have been public and unusually fast. In 2021, Broad assembled a 10-story apartment building it called the Living Building in Changsha in 28 hours and 45 minutes. In January 2024, it completed the 26-story Jingdu Tower in Shangyin County in 5 days, turnkey, including utilities and its own energy recovery ventilation system at around 14,000 square meters. And in December 2025, the same system produced a 16-story residential tower called Earth Tower in Abu Dhabi for the developer Eagle Hills, made up of 259 container-sized modules manufactured in a 30-day factory run in China and shipped in about 20 days. The developer described costs comparable to conventional construction and said further towers of 15 to 30 floors are already being planned. Quick question before we go on, because I am curious how split people are on this. If a factory could ship you a container-shaped module that unfolds into a properly insulated, non-rusting home twice the width, would you take that over a converted shipping container, even if it cost a bit more upfront? Or does the used 40-foot box for a few $1,000s still win on principle? Tell me in the comments. And if you like videos that dig into how ordinary things actually work, subscribing genuinely helps this channel keep making them. Now let us be honest about where this really stands, because the gap between what exists and what you could buy is wide. The first problem is that none of this is currently sold to individuals. Everything Broad has built with this system is multifamily, mid-rise, or high-rise, aimed at developers ordering hundreds of modules at once. The economics are built around a production line, not a customer. There is no single unit product, no price list, and no announced plan for one. The second problem is cost, and this is where independent analysis is most skeptical. Stainless steel is significantly more expensive than the carbon steel used in shipping containers and conventional structures, and a hull-on building uses a very large volume of it. Reviewing Broad's own most optimistic published pricing, Construction Physics concluded the numbers still came out above average American construction costs, while also flagging the quoted transportation fees as unrealistically low. Cheap for a dense city with brutal build costs is a very different claim from cheap for a plot of rural land, and the second claim has not been demonstrated. Third, manufacturing. Brazing thousands of thin-walled tubes between stainless sheets with copper foil is a precision process that currently happens in Broad's Chinese factories. The company has said it intends to open factories in destination markets, including the United States, but that has not happened at scale, which means today every panel is a shipping and tariff question as well as an engineering one. Fourth, and least glamorous, is approval. Container homes already run into this constantly, with zoning boards, appraisers, and lenders treating them inconsistently from one county to the next, sometimes classing them closer to mobile homes than to houses. A stainless steel modular system with no concrete in it is newer and less familiar than a container, not more. Building officials tend to move at the speed of precedent, and precedent is exactly what a new structural material does not have. And it is worth noting the company's own history, because it cuts both ways. In 2012, Broad broke ground on a proposed 838-meter tower in Changsha, intended to be the tallest building in the world, and built from modules in a matter of months. It stalled almost immediately over approvals and safety concerns and was never finished. A company that has made extraordinary claims before deserves both the credit for what it has actually completed and the skepticism for what it has not. So no, the shipping container home is not obsolete tomorrow. What is happening is quieter than that, and in some ways, more interesting. The conversation is shifting away from how do we repurpose a cargo box into a home toward a different question entirely, which is what would a box actually look like if it had been designed for people from the very beginning? And what if it happened to keep the container's dimensions purely because the world's ports and cranes and trucks are already shaped around them? That shift shows up in more places than housing. Across a lot of industries right now, the pattern is the same. Someone looks at an object everyone has quietly accepted, finds that its shape was determined by a constraint from decades ago, and asks whether the constraint is still real. Sometimes the answer is that the shape was never the point. The shape was just the packaging. There is something a little uncomfortable about sitting with that. Millions of people have spent the last 20 years turning cargo boxes into homes, and doing it well, and solving genuinely hard problems with insulation and reinforcement and clever layouts, all in service of an object that was optimized in 1956 for the specific task of not being opened until it reached the other side of an ocean. It worked. It just may turn out to have been the long way around. Real changes in construction almost never arrive as a single dramatic reveal. They arrive as a material spec sheet nobody reads, a factory line that gets slightly faster every quarter, and a building that goes up somewhere far away while everyone else is looking in a different direction. So here's the question I will leave you with. What else in your life is shaped the way it is, not because that shape is right, but because of a limitation that stopped being true a long time ago and nobody bothered to check? Let me know in the comments. And if you want to keep finding the engineering hiding inside ordinary things, subscribe so the next one finds you.